In this video, we will be talking about the normal distribution. Before you continue watching this video, you should read in your textbook about continuous random variables, and make sure you understand the difference between a continuous random variable and a discrete random variable. Having read the section on continuous random variables, one of the key facts that you should have noticed is that if x is a continuous random variable, the probability that x equals some specific value c is always 0. This is very different from the discrete random variables we have been working with up to this point, where, for example, if x represented the random variable associated with rolling a six-sided die, the probability that x equals 2, for example, is equal to 1/6. So for discrete random variables, the variable can actually take on a specific value with a positive probability. For continuous random variables, the probability that a continuous random variable takes on a specific value is always 0. Recall from our section on expected values that a random variable, if it's a discrete random variable, has a probability distribution, also known as a probability mass function. And if you have a finite sample space, as all of our examples have been, you can represent this probability mass function as a table. Continuous random variables have probability density functions, or PDFs. A function f of x is a probability density function if the area between the function and the x-axis equals 1. Recall that with a continuous random variable, the probability of that random variable taking on a specific value is 0. But there is a probability that it will take on a value within a range of values. So suppose that x is a random variable with probability density function f of x. Then the probability that x takes on a value between a and b can be found by finding the area under the probability density function f of x between the points a and b. This idea is consistent with the probability of a continuous random variable taking on a single value being 0. If we look at a specific x, then the area under the curve for just a single point is 0 because it's simply a vertical line, and a vertical line has no area. It needs width before it'll have area. A normal random variable is a continuous random variable whose PDF forms a bell curve. For those who are interested, the precise formula for the bell curve PDF is given in your textbook, but we won't actually need to use that formula. Since a bell curve is a probability density function, the area under a bell curve always equals 1. So therefore, both the red area and the blue area add up to 1. The highest point of a bell curve occurs at the center of the bell curve, and this turns out to occur at the mean of the normal random variable represented by this bell curve. Recall that we used sigma squared to represent a population variance and s squared to represent a sample variance. Well, x bar, the symbol that we've used for the mean, is the sample mean, and we use mu to represent the population mean. So the center of a bell curve occurs at mu, the mean of the normal random variable. Another property of bell curves is that the area to the left of the mean is half of the bell curve, and since the entire area is 1, it equals 0.5, and the area to the right is 0.5. So what that tells us is we already know some probabilities for any normal random variable. The probability that x is less than the mean equals 1/2. The probability that x is greater than the mean also equals 1/2 if x is a normal random variable. Looking at our two example bell curves, we can immediately see that normal random variables can have different means. But also notice that the normal random variable represented with the red mean is narrower in its bell curve than the normal random variable represented with the blue mean. This tells us that the bell curve with the red mean has a smaller variance than the bell curve with the blue mean. the data points are more spread out on the blue curve than they are on the red one. So the two pieces of information we need to specify a specific normal random variable is the mean and the variance. And it turns out that these are the two parameters needed for the PDF function to represent any bell curve. We'll use the following notation to indicate that x is a normal random variable. X is distributed as a normal random variable with mean mu and variance sigma squared. Let's look at an example. If I write that x is distributed as a normal random variable with mean 3 and variance 25, then what I know about x is that x has a mean of 3 and a variance of 25, which tells me that the standard deviation is 5. It's important to be able to compute the standard deviation given the variance because we'll use the standard deviation in our calculations, not the variance. It turns out that computing the area under a bell curve is a difficult task. So most people have to refer to tables to find areas under bell curves. But we have a different bell curve for every different mean and variance possible. Now, mean can be any number, positive or negative. Variances are always positive numbers, but that still gives us infinitely many different possible bell curves. And we can't have a book with infinitely many tables in it. The solution is that we have a specific normal random variable which we call the standard normal. We'll use z instead of x when we want to represent the standard normal. Z is distributed as a normal random variable with mean 0 and variance 1. So the standard normal has a mean of 0 and a variance of 1. If the variance is 1, then the standard deviation is also 1. So then we'll have a table for standard normal random variables. And it turns out that there's a formula which will convert any normal random variable into a standard normal. And we can use that to create probability questions in the standard normal format, which we can use the table to solve. Let's look at an example of a standard normal probability question. So again, z represents a standard normal random variable. Suppose we want to find the probability that z is less than 1.27. Here's a picture of the area that we would want to find to answer this question. We're looking for the area under a standard normal bell curve. Remember, the mean is 0, so it's centered at 0. And we're trying to find the area of all values that are less than 1.27. So we find 1.27 on the z-axis, and then we find every value less than 1.27, and we're looking for that area. The table provided in the appendix of your textbook is the standard normal CDF table, where CDF stands for cumulative density function. Remember, we like to think of reading graphs from left to right. What a cumulative density function does is, given a specific value, it gives you the total area under the curve up to that value. Now, the CDF table in the appendix only provides the CDF for positive values of z, not negative values. But it turns out you can use the symmetry of a bell curve, the fact that it's perfectly symmetric on both sides of the bell curve, to solve for negative values. And we'll look at an example of that in a little bit. So this area is precisely the area that the CDF table provides. Here's a small portion of the table provided in your appendix. That way we can see how to use the table to find this area. So notice that the first two digits, the whole number and the tenths place of the number, is listed in these rows. And the columns give you the hundredths. So if I'm looking for the area up to 1.27, I go down to 1.2 and all the way over to 0.07 for 1.27. This gives me the total area under the curve up to 1.27, which is the probability I'm looking for. So this probability is approximately equal to 0.89796. What this means is that for a standard normal random variable, the probability that that random variable will take on a value less than 1.27 is 0.89796 roughly. So about 89.8% chance that this random variable will take on a value less than 1.27. So we can use the table to immediately find the probability that a standard normal random variable is less than some positive value. Well, what about the probability that a standard normal random variable is greater than some positive value? It really helps if you have a picture of what this area is that you're trying to find. Now the picture doesn't have to be sophisticated like our previous example. You can simply draw it by hand. You know that a standard normal is centered at 0. 1.27 is some value greater than 0, so it's on the right side of 0. We're looking for numbers bigger than 1.27, so that shaded region is the region I'm looking for. Now we know how to find the total area to the left of that positive number. It was 0.89796. And we know that the total area of the curve equals 1. So then this area that we're looking for can be found by taking the total area 1 minus the 0.89796, the portion of the curve we're not interested in. This gives us an area of 0.10204. So the probability that a standard normal random variable is greater than 1.27 is approximately 0.10204. What if we want the probability that a standard normal random variable is less than a negative number? Again, drawing a rough sketch of the curve can really help. Centered at 0, negative 1.27 is a number to the left of 0. We want everything less than that. Because of the symmetry of the bell curve, this area is equivalent to this area. So we can flip the curve around, solve for the area in the previous example, and we'll get our answer. And we know that this area is 0.10204. Likewise, if I wanted the probability that a standard normal is greater than negative 1.27, I can draw a rough sketch of the curve, centered at 0, negative 1.27 is over here. I want z's bigger than that number, so I'm looking for this area. And using the same logic we used before, this is equivalent to finding this area, the first problem we solved. So that's approximately 0.89796. What if we're trying to find the following probability? The probability that a standard normal is between negative 1 and 1.2. Again, we want to draw a rough sketch of the picture. Then, we need to do a little creative thinking. I know how to find the blue shaded region. This is the probability that a standard normal is less than 1.2. Unfortunately, that has a little more area than I'm looking for. But I also know how to find the region shaded in red. That's the probability that a standard normal is less than negative 1. So if I find the area shaded in blue, and I subtract off the area shaded in red, I'll be left with the answer I'm looking for, the area shaded in black. Why don't you go ahead and try to work this out on your own? Solving the two pieces that we discussed would work as follows. The probability that z is less than 1.2, that's the total area to the left of 1.2, so I can use the table directly. Looking up 1.2 in the table, I find that that probability is 0.88493. The probability that z is less than negative 1, to get the red shaded region, well, if we draw the bell curve, we see that it's the total area to the left of a negative number, which is equivalent to the total area to the right of the positive version of that number. And we know to find the total area to the right of a positive number, we take the entire bell curve and subtract off the area to the left of that number. So the entire bell curve is 1, and we subtract off 0.84134, which is the total area to the left of 1. So the probability that z is less than -1 is approximately equal to 0.15866. So the area we're looking for can be found by taking the blue shaded region and subtracting off the area of the red shaded region, for an approximate area of 0.7263. Tables are still used in practice, but modern technology allows us to find the area under a standard normal bell curve using our calculators. Your textbook will explain how you can do this using a TI-83 or 84 calculator. There is a difference, though. The CDF table gives us the total area to the left of a positive number. It turns out that the calculator has decided to give us the area between two numbers. So problems that are easy using the table actually become a little more work using the calculator, whereas problems like we just solved using the table, which required a bit of work, turn out to be the easier problems on the calculator. You should make sure to verify which method your instructor will expect you to use on exams. Some instructors may require that you use tables, some may require that you use the calculator, and some may allow you to use either method. So now we've seen how to solve probability questions with standard normal random variables. But it turns out that in practice, most random variables are not the standard normal. For a random variable to be a standard normal random variable, it must have a mean of 0 and a variance of 1. And in practice, not many things have a mean of 0 and a variance of 1. Well, if x is distributed as a normal random variable with mean mu and variance sigma squared, it turns out that there's a formula which will convert this normal random variable into a standard normal. And it goes like this. If you take x minus the mean and divide by its standard deviation, you will have a standard normal random variable. So how would I use this formula in practice? Suppose that x is a normal random variable with mean 2 and variance 9. Again, recall that this means the mean is 2 and the variance is 9, which tells us that the standard deviation is 3. And suppose that I want to find the probability that x is less than 3. Well, this is equal to the probability that I can take x minus the mean divided by the standard deviation and do it to both sides of the inequality, so 3 minus the mean divided by the standard deviation, which is equal to the probability that now that I've taken my normal random variable, subtracted off its mean, and divided by the standard deviation, it is now a standard normal, is less than 1/3. And this is precisely the type of problem that we just learned how to solve previously. Turns out this is approximately equal to 0.6293, in case you want to try that out on your own. Let's try another example. Suppose x is distributed as a normal random variable with mean 2 and variance 5. Then what's the probability that -1 is less than x is less than 1.35? Why don't you try to convert this to the equivalent standard normal question? So pause the video and try to write down the standard normal question that's equivalent to this. Using the same technique we used before, this is equal to the probability that -1 minus the mean divided by the standard deviation is less than z is less than 1.35 minus the mean divided by the standard deviation. Now we would just need to solve this standard normal question. Now you're going to want to find decimal approximations for the number on the left and right side of the inequality. And then you can go ahead and solve this the way we've solved the others. And you should get that your answer is approximately equal to 0.2958. At this point, you should make sure that you read the section in your textbook that gives applications of normal distributions. The only difference between an application problem and what we've just done is that you need to take the words from the application problem and write down both a normal random variable and a probability question for that normal random variable.